Hey folks, we are starting section 6.3 today. Let's go ahead and dig in. So let's V and W be vectors that are in Rn. We're going to define what's called the orthogonal projection of V onto W in two ways. I'll start with the formal mathematical definition, and then we'll look at a less formal definition here. So the formal definition, the orthogonal projection of V onto W, and it's written like this. It is the abbreviation of the word projection. V is the vector that's being projected. The little subscript W is the vector being projected onto. It is a multiple of W chosen so that the magnitude of this difference vector is as small as possible. So if this is the vector W and this is the vector V, well, the vector V minus W is the same as V plus negative W. So negative W would be pointing in this opposite direction. This would be V minus W. And so that would be the vector V minus W. We go up V, we go back 1 negative W. And I want to make this vector as short as possible. Well, there's a way to do that. That is, no matter how much I scale W by, if I double W, it's out here. If I take just half of W, it's in here. And the vectors that we get look like these. And the shortest one will be the one that makes a perpendicular. And we're going to use that perpendicular to come up with an easier definition to use rather than trying to turn this into a calculus problem where we're trying to minimize something from the distance formula. We can do it that way. We can use this definition and find the global minimum of this function here. But it's faster to use the dot product. So to minimize the distance, we want to travel at a right angle to the target, which gives us this more useful definition. It's not as formal, but it's more useful. Draw V and W so that they share the same tail. We've already done that. So if this is W and this is V, construct a perpendicular line from the head of V through the line that contains W. So we're just going to draw a perpendicular that goes through V and through that line. That's the construction we're going to put on. The orthogonal projection of V onto W is the vector from this tail to the point where the perpendicular intersects. And so that little piece right there is the projection of V onto W. It's that little piece right there. So let me show you a couple of examples. Here are two examples of orthogonal projections. So in this example, W is rising slightly, has a slightly positive slope. So I draw a line from V down to W at a right angle, and the projection is the leg of the triangle that we get. So in this example, it looks like this is about half of W. It's not all of W, it's maybe a little bit more than halfway. In this example, vector W is pointing in this direction, but this angle is more than 90 degrees. And so when we draw the perpendicular to this line, the perpendicular is actually on the other side, And so this is roughly about negative 1/2 of W. Again, maybe a little bit more than half, but it's pointing in a different direction. And so the orthogonal projection can be in the direction of W, or it can be in the opposite direction to W, depending on whether this is an acute angle or an obtuse angle. Both of those are possible. All right, let's move on. We can use trig to solve for the orthogonal projection. Let me go back to this sort of diagram here where this is W and this is V. And we drop our perpendicular line right here. And this piece right here is the projection of V onto W, that little piece right there. But this is the adjacent side of a right triangle. This is the hypotenuse. And so the cosine of this angle is equal to the projection of V onto W divided by V. And actually, these are vectors. I have to take their magnitudes. And then bring this to the other side. The length of the projection is equal to the magnitude of V times the cosine of the angle. So we could use that and solve this problem using trig. So the projection, if this is just the length of the projection, then we multiply that length times a unit vector, and we will get the vector that we want. This is a unit vector because we scaled out the length of W. So if this vector has a length of 1 and this has a value of, say, 5, we multiply these together and we get a vector of length 5. And so this formula is correct, but an easier formula is coming. In chapter 6.1, you may remember that we had a formula for the cosine of theta. So we're going to use that formula, that the cosine of theta is the dot product of the two vectors over the magnitude of the two vectors. And let's look at what happens here. This is the magnitude of V times the cosine, which is dot product of V and W, over the magnitude of V times the magnitude of W. These will cancel. And what we have here is the magnitude of W squared. And so I want to talk about this for a second. Let's say W is some vector ABC. Then the magnitude of W is the square root of A squared plus B squared plus C squared. It's the Pythagorean theorem. So then the magnitude of W squared, which is what we have here, just makes the square root go away. But that's the same thing as W dot product with itself. A dot A is A squared, B times B is B squared, C times C is C squared, and we add them together. And so that's where we get this W from. So we get the dot product of V and W. This converts to the dot product of W and W, and then we have one W that's left, which is over here. And so this formula, let me clear out some of my scratchies here, is faster because it doesn't require us to use any trig at all. We can do this without having to do any cosines or angles or anything like that. So also works and there's no trig. Okay, so we dot product the vector that we're projecting with the vector we're projecting onto. We divide by the dot product the vector we're projecting onto with itself. And then that's going to give us a scalar, a number. We will take that number and multiply it by the vector w. And on the next slide, I'll work through an example. All right. So we have these two vectors. Let's compute the projection. So here's our definition. The projection of w onto v is the dot product of both vectors divided by the dot product of w with itself times w. So w shows up 4 times in this formula and v only shows up once. So in the numerator, we're going to dot product both vectors. So this is going to be 3 plus 0 plus 4, which is 7. And the denominator, we're going to take w dot w. So that's going to be 1 plus 9 plus 4. And then this w is just a vector 1, 3, 2. We're not doing anything with that. Well, this is 7 on top and 14 on the bottom, which is the same as 1/2. When we take 1/2 of this vector, we get 1/2 and 3/2 and 1. And that is the projection that we want. We have the exact answer. We did not need to use a cosine. We didn't need to use any trig at all. Linear algebra has given us a fast way of computing the adjacent side of this right triangle. Okay? All right. Let's move on. So let's suppose that we have a vector that's in Rn, and we have, instead of a single vector, we have a subspace. We can define the projection of V onto that subspace the same way that we define the projection onto a vector. So let me draw you a picture of what might be going on here. So let's say my subspace is a plane. It's the span of 2 vectors. And my vector v is, say, coming out from this, and it doesn't lie in the plane. But if I drop a perpendicular onto the plane, and I look at the vector that comes out to where that perpendicular meets, that's the projection of v onto the entire subspace W. All right. So how can we define that? Well, it's going to be based on the idea that we just had let me back up 2 slides. This formula gives me the projection onto a single vector. What we're going to do in this problem is we're going to find, this is a formal definition, that we want the vector so that the magnitude is as small as possible. Instead of using calculus to find the global minimum of this function, we're going to use the orthogonal projection formula that says use the perpendicular here. Okay? So here's a diagram. All right. If we have a basis for W, and it's an orthogonal basis, and we define that in 6.1, it means that not only is it a basis, but the vectors are orthogonal to each other. Then the orthogonal projection of V onto the subspace, onto the subspace is the sum of the orthogonal projection onto each of the basis vectors. We project V onto W1, we project V onto W2, we project V onto W3, W4, W5, however many W's we have in the basis, and we just add them all together. So projecting onto a plane is a span of two vectors. We just do two individual projections and we add them together. So it's not more complicated than projecting onto a vector. It's just longer because we have more directions that we have to cover. So let's try an example. So let's look at W1 and W2, and W is a span of these two vectors. So first of all, what I want to check is W1, W2, and orthogonal basis. So the dot product of W1 and W2 is 0 minus 1 plus 1, which is 0. And so, yes, it is. Because these vectors are orthogonal, then we can use this shortcut formula to compute the projection. And so the projection of V onto W is going to be, we're going to project V onto W1, and we're going to project V onto W2. And we're going to add them together. So this is V dot W1 over W1 dot W1 times W1 plus V dot W2 over W2 dot W2 times W2. So we just have to project onto both basis vectors, add the totals together. All right. So V dot W1 is going to be 8 plus 0 plus 4. W1 dot with itself is 4 plus 1 plus 1. And W1 is 2, 1, 1. And then over here, V dot W2 is going to be 0 plus 0 plus 4. And then W2 dot with itself is 0 plus 1 plus 1 times W2. So this is 12 over 6 times 211 plus, and this is 4 over 2 times 0, negative 1, 1. And so 2 times this vector is 4, 2, 2. And 2 times this vector is 0, negative 2, 2. When we add them together, we get 4, 0, 4, which turns out to be V itself. So what does that mean when V projects onto itself? Well, it means that W contains V. That is, V is already in W, and so the perpendicular is just, well, there's no perpendicular, it's like a dot. It's a triangle that has collapsed downwards so that the adjacent side and the hypotenuse are right on top of each other. And so this is a way indirectly it shows that V is in W. Okay? This won't usually happen. Most of the time, V won't actually be in W, but it can be, and this is what happens when V is in W. You get V as the projection. All right. So let's try this again. Let's look at these two vectors. W is the span of the two vectors. First, let's check to make sure that W1 and W2 are perpendicular, because we do need an orthogonal basis for this to work. So W1 dot W2 is -4 plus 5 minus 1, and that is 0, so that does check. And now let's project the W onto V. So the V onto W. Projection of V onto W is, all right, that's the projection of V onto W1 plus the projection of V onto W2. So that's V dot W1 over W1 dot W1 times W1. And then same thing, project V dot W2 over W2 dot W2 times W2. Okay, so let's look at this dot product. V and W1 is going to be 2 plus 10 minus 3. W1 with itself is going to be 4 plus 25 plus 1. And W1 is 2, 5, negative 1. All right. V dot W2 is going to be -2 plus +2 plus 3. And then W2 dot with itself is 4 plus 1 plus 1. And then W2 is -2 and 1 and 1. And I'm sure you caught my error over here. No, this is okay. 2, 10, and -3. All right. So let's see how this goes. 12 minus 3 is 9. 29 plus 1 is 30. And then this is 3 over 6. Nine over 30 reduces to 3/10, which is 0.3. And so if I multiply this vector by 0.3, we get 0.6, 1.5, and -0.3. When we multiply this vector by 1/2, we get -1, 0.5, and 0.5. When we add these together, we get -0.4, 2, and 0.2. And that is the projection that we're looking for. All right. So just looking ahead, we now have a procedure that's not super complicated to project a vector onto a subspace, as long as the basis for that subspace is orthogonal. What we're going to look at in the next group of slides is, what if the basis is not orthogonal? Can we still do this? And the answer is yes, because we will discover a technique in 6.4 that will take a basis that's not orthogonal and convert it to a basis that is orthogonal so that we can do this. And so that's what we're going to be doing next time. is this question again, but what if the basis is not orthogonal to start with? Thanks for watching. I'll see you around next time. Bye-bye.